should be on.
Slides are on, great. So let me introduce Iacopo Carusotto. It's our pleasure to have you here. I'm very happy about this. Iacopo did his undergrad in Pisa, where he is from also, and stayed for a PhD studying optics in semiconductors and as well as in the atomic systems. And already in this time, he started collaborating on the exchange also with Jean Dalibard and Ivan Castin in Paris. And this is also where he went back then for a postdoc, for a Marie Curie postdoc to Paris in the group of Cohen Tanucci, and again working with Jean Dalibard and Ivan Castin. And then already like in 2003, Iacopo became a tenured track researcher in Trento. And again, like had there like a couple of stays at in Paris and also in the group of Atachi Mamuklu at ETH then. But then since then, Iacopo has been a senior researcher and professor in Trento. So his work has gotten a lot of attention, for example, like the Birds of Art offered by the Institute of Physics for a young and coming theoretical physicist, and he also was awarded a prize by the Italian Physical Society in the same year. So today, it's our pleasure to have him talk on new trends in topological physics, where he, I think, will explore how like new topological effects appear in wave mechanics and in quantum many-body systems. Iacopo.
Thanks a lot, Valentin, for the invitation. It's really a great honor for me to be with you tonight, or today for you. And it's what I'm going to present with you is a kind of overview of new topological physics that can be done using optical systems. So the idea is to give you a kind of general idea of the field. So please feel free to interrupt me anytime you wish, whenever you have questions. More interactive is the talk, the more fun it's for all of us. Good. So the idea where I started from was something well known in condensed matter physics, which is the fractional quantum Hall effect, which is a very intriguing effect which takes place when a two-dimensional electron gas, which lives on the surface of some semiconductor, is exposed to a very strong magnetic field and is cooled at very, very low temperatures. So the interesting observation is that if one measures the Hall resistivity, which is related to the voltage drop across the current direction, this guy shows plateau at very well-defined integer or rational multiples of some combination of fundamental constants. And the position of this plateau is associated to some zeros of the longitudinal resistance, and they are at positions which are immune to disorder. And what's even more intriguing is that the width of these plateaus is made better when the disorder is increased, of course, up to some moderate level. So it's an effect where one has a physical quantity which is quantized to some rational value independently of disorder, and disorder even helps the manifestation of this effect. So this is an extremely striking effect of condensed matter physics, which required a lot of efforts to find a theoretical justification. It comes from a very peculiar interplay of electron-electron interactions and quantum mechanics in the presence of strong magnetic fields. But the question that I started wondering in the mid-2000, late 2000 was how this kind of physics can be observed using different particles, so something different from electrons. Can one see some fractional Hall physics using quantum fluids of light? So fluids where the elemental object is not a material particle like an electron or a helium atom or a neutron, a proton, or whatever material object. No, it's a photon. So it's a gas of photons, which interact with each other via the optical nonlinearities of the medium, and in this way can display some collective phenomena. So this was the start point of all my thinking, together with plenty of colleagues. And as I will tell you in the talk, this idea has grown into something very exciting, which has very promising directions of growth in the next years. So the structure of the talk is a beginning. I will try to explain you how magnetic forces such as Lorentz forces can arise for neutral particles like photons. And I will discuss how these can be used to study topological effects and integer quantum Hall physics. Then I will move towards some application of this physics for devices, opto-electronic devices like laser operation in topological models, the so-called topolasers. And then in the last part, we'll enter the world of many-body physics in the direction of fractional quantum Hall effect to see how these strongly correlated gases or photons can be actually realized in some experimental platforms and how can they be used to probe new physics. Very good. So let's start with a brief journey through topological photonics. If you want to have a kind of general look at the field, I recommend you to have a look at this Review of Modern Physics paper, which was first authored by Tomoki, who was at the time a postdoc in Trento, and together with Hannah Price, which was the other leading author. This paper tries to summarize all the state of the art of topological photonics at the time of late 2018. Good. So my interest in this topological photonics stuff came having in mind what was being developed in the atomic context. So since I was a kid, I heard about the idea of putting atoms in a rotating trap so that the Coriolis force mimics the Lorentz force of a magnetic field. And in this way, one can create some magnetic effects. Here is an example of an experiment done in the group of Jean Dalibard. At the time I was there as a postdoc, where Vincent Bretin was able to generate a lattice of vortices in a rotating BC. And since then, there's been a lot of efforts to push these experiments further into a regime of few particles, strong interactions, where atoms get into a fractional quantum Hall state. For technical reasons, this showed up to be much more difficult than expected, but at the same time, it gave a good motivation to develop other schemes to generate magnetic effects with atoms. And here is a brief list of some most exciting results. We have shaken lattices giving rise to Haldane model for atoms, Floquet physics. There's been laser-assisted hopping to create Harper-Stetter models. There's been synthetic gauge fields by a combination of Raman and static magnetic fields. And there's been the idea of synthetic dimensions to go beyond the physical dimensions that everybody knows into something more subtle and more interesting in even 4 dimensions, as it is sketched in this plot. So these are all developments that are being carried out in the atomic community. But at the same time, there's been a very big and strong boost in this physics in the topology, in the photonics context. Here, everything started with this seminal theoretical paper by Duncan Haldane and Raghu, who basically translated the ideas of integer quantum Hall effect into the world of optics. So basically, their paper is based on the idea that the integer quantum Hall effect depends on the geometrical properties of the Bloch band states such as the Berry connection, the Berry curvature, the Chern number, and blah, blah. And all these things do not depend on the physical nature of the particle under examination, but can be extended also to other particles like photons, provided their bands are non-trivial. So the real objective is to generate band structures which are complex enough to host non-trivial Chern numbers. So to have a Berry connection which characterizes the structure of the eigenstates, this has to be complex enough to give a non-trivial topological invariant. To have this quantity different from zero, of course, one needs to break some asymmetries, particularly time reversal. But in optics, this is not a problem. It's enough to use some magnetic element in your device, and T reversal is automatically broken. Of course, in photonics, one cannot make a measurement of current, so one cannot measure the whole current as it was done with electrons. So one has to find some more clever observables. And indeed, in this paper by Haldane and Argood, there was a proposition of using one-way waveguide modes living on the edge of the system. Experimentally, this was realized not long afterwards in the group of Marin Soljacic at MIT, who used a photonic crystal, which is an arrangement of a periodic arrangement of different materials. Here is the sketch of the experimental system. It's a 2D photonic crystal enclosed between two slabs of two metallic plates, which confine the electromagnetic field in between. And in between there is a lattice of pillars of magnetic elements. It's a magnetic material where the polarization, the dielectric polarization depends on the circular polarization of the applied electromagnetic field. So sigma plus, sigma minus polarization of electromagnetic field feel a different dielectric susceptibility. And this is enough to break time reversal. In this way, one can calculate the bands. So the bands are plotted here as a function of a wave vector along one axis. The other axis is just squeezed, as one typically does in these kind of band structure calculations. One sees the lowest band with zero Chern number, a non-topological gap. The second band has a Chern number of 1, so there is a topological state on top of it. Then the next band has a -2 Chern number, and there are more and more topological edge states. So this state, plotted in red, is a topological edge state, which lives on the edge of the system and propagates with the group velocity, which has a well-defined sign throughout the first Brillouin zone. Which means that if one shines light or emits an electromagnetic wave in this system at antenna A, electromagnetic waves will only propagate in one direction. You see here is the result of a simulation. Antenna is at A, emits light at a frequency which is chosen to be in resonance with this red mode, and light propagates only to the right. Nothing goes back. So this behavior is strongly non-reciprocal. In a non-reciprocal configuration, you can see me, but I cannot see you. So light only propagates in one given direction. This effect is even more striking if you put a defect along the way of the photons, because in this way, the photon emitted from A propagates towards the defect, and instead of being reflected back, as it happens when you put a mirror on the path of a laser, here the light goes around the defect and keeps propagating along the edge in a unidirectional way. So this is a chiral mode, chiral because it goes with a given chirality around the system. Unidirectional, which is equivalent, it goes only in a single direction. And this chiral unidirectional propagation is related to topology and is called topologically protected because it's not too much disturbed if the material is imprecise. So any, say, roughness does not give rise to a distraction of this mode, it just go around the defect, almost unperturbed.
Sorry, can I just interrupt? Like you have these bands in the top figure. Like what? Yeah. Like why is there, like, what's the shading in between the?
Here basically you see this is a two-dimensional bands, and this is a wave vector along one direction.
Okay.
So the shading corresponds to all the states with the different values of a wave vector in the other direction.
Ah, okay, all right, good, thanks.
Yeah, that's just it. And this is an edge state, which is a single state because there exists only a single edge state per wave vector along the interface.
Sure,
so
thank
this
you.
State lives on the edge. And here, the experiment by the group of Marine was basically that light going from B to A is basically forbidden. Nothing happens here in the gap, while light from A to B can propagate almost freely. Of course, there is some perturbation, some impedance mismatch, and some problems, but there is a substantial light propagation from A towards B, so rightwards. On the leftward direction, there is nothing going on. And this is a proof of being unidirectional. Of course, this experiment had some limitation. It was a very pioneering one. It required magnetic material, and it was not able to image the propagation of the edge state. So the new generation of experiments, a few years after, was aiming at doing this physics without magnetic materials in the visible domain and trying to image the edge state. This was done almost simultaneously by two groups, one by Mehmet Afetzi at JQI, and the other one in Israel in a group of Moti Segev and Alex Tzamait. And here are the pictures of Mehmet Afetzi's experiment, where he basically drives the system on this cavity, and he sees that light goes on this direction only. Here is experiment, here is the theory. Interesting enough, he put a defect here, and he saw that light hits the defect, goes around the defect, and keeps going on the edge. Exactly as one would have expected from the theoretical calculation. This is an example of one-way propagation along the edge. The interesting point of this experiment by Mehmet is that he uses purely dielectric material, and it works in the visible. So you may wonder, how can he see topology with a system which does not break time reversal? Actually, the system is not really non-zero Chern number physics, is more of a kind of spin-hole effect. So each of these sites in reality hosts two states. One can be seen as an up state, spin up, and the other one is a spin down. So the spin up states propagate in this direction, spin down states will propagate in the opposite direction. But here the experimentalists were smart enough to find a way to excite only one of the two class of states. So light only goes in one direction. So this was an imaging of the edge states, which according to the original Haldane proposal is the smoking gun of the non-trivial topology. Of course, the topology contains much more than that. There is also the physics of the bulk. So you know the semi-classical equation of motion for a particle in a lattice. Normally you have the derivative of momentum is given by the applied force, and the derivative of position is given by the derivative of the energy bands, so the Cook velocity. But in the presence of a non-trivial Berry connection and Berry curvature, one has this additional term of the velocity, which is called the anomalous current. This anomalous current can be seen as one of the origins of the integer quantum Hall effect. Here are experiments done to observe this term with ultra-cold atoms. For photons, the first experiment was carried out in Jena in the group of Wolf-Peschel. The first author is Martin Wimmer, with the collaboration of my group for theory. Hannah Price was really the big energy in this idea. So the system under consideration is a so-called optical mesh lattice, which is composed by a pair of waveguides coupled by the 50-50 beam splitter. So one has light pulses going around these optical fibers, and the wave packet at each loop can choose whether to go on the long fiber or on the short fiber. In this way, each time it makes a loop, it can move in time according to which of the two paths it has followed. So this, the arrival time of the photon after a given number of round trips can be seen as a special position in a one-dimensional lattice. So this is a way to simulate a one-dimensional lattice using just a pair of waveguides. The number of round trips is a sort of time. The exact arrival time is the spatial position. So these optical mesh lattices have been used a lot by the group of Wolf-Peschel, but also by many other groups. And they have the very interesting feature that can be scaled up to any dimension just by adding more and more pairs of optical fibers. So here is the simplest case, 1D, where Hannah and Martin were able to obtain a band dispersion which shows a non-trivial Berry curvature. So when you have a non-trivial Berry curvature and you push the wave packet around in on the band, you should see a lateral shift of the wave packet following the Berry curvature. And indeed, is what the guys in the lab observed. Here you see that the wave packet is pushed in this direction towards the right as time goes on. M is time, N is position. But you see that depending on the value of phi naught, which is basically a sort of external magnetic field, you can have two paths which seem very similar, but in reality they are slightly different, signaling a small shift which depends on the Berry curvature. This small shift can be quantitatively analyzed and can be compared to the expected Berry curvature of these bands. Here is the theory of the Berry connection done by Hannah, and here is the experimental measurement of the Berry curvature obtained by this tiny shift. And you see that the qualitative structure of the Berry curvature distribution all over the Brillouin zone is very well reproduced. Here is as a further check, they did the experiment with the second band of this system, and indeed the result is that the Berry curvature is exactly the same with the opposite sign. So this is an experiment showing the Berry curvature of the photonic bands in a complex lattice, which somehow completes our view of the bulk boundary correspondence. There were the boundaries, and here is the bulk. So this is a sort of general idea of what can be done with photons at a linear level. Now let's move on with some nonlinear effects. What is the most well-known, the strongest, the most exciting nonlinear effect is lasing. Basically lasing, when you endow a system with some gain, particularly topological lattice, you can get the system to lase on the edge states of the topological system. This is a topological edge state lasing, in short, topological lasing. The first experiment in this direction was done by the group of Alberto Amo and Jacqueline Bloch in Paris and Lille. The first author is Philippe Saint-Jean. And they observed lasing in the edge states of a one-dimensional chain. This is a lasing in an isolated state. It's a zero-dimensional edge state of a 1D chain. Very interesting, but there is not rich physics. The physics becomes much more exciting when you have a one-dimensional edge state on the edge of a two-dimensional lattice. Here is the first experiment by Boubacar Kante's group at San Diego, where they showed they used a photonic crystal under a strong magnetic field, and they saw topological lasing on the edge. Here, this photonic structure is designed in the shape of a United States map. You see that this lasing mode goes around the US and comes out from the Gulf of Mexico and goes back towards Europe. So it's a sort of Gulf Stream of photons exiting the US from the south. Here is just a sketch, here an experimental result. Another experiment, which does not make use of magnetic elements, is based on the Hafezzi platform, and the experiment was done in the group of Mott with Miguel Bandres as a leading author, using an array of silicon cavities with this extra element to break parity symmetry. Again, the result is that lasing occurs on the edge state in one preferential direction. So this system is a realization of this topological lasing idea. But what is new in these systems? Why are these systems so interesting? So one knows that there is a big problem in laser physics of having a spatially extended device which simultaneously is able to emit high power and coherent light. So to join high power and coherence. So you may think in a very naive way that you take many lasers, you put them together, and they will start lasing in a common mode, in a mode which is common to all of them and will phase lock. Unfortunately, this is not true. People have made huge efforts in trying to get an array of cavities to lace together in a phase-locked way, but most efforts have failed. So here is a result of a simulation, and you see that basically you get a mess. Each site emits independently from the others. The system is extremely sensitive to disorder. There is no phase locking. So basically you get a big potato in the emission spectrum, which is not of very use if you need some good laser source. Even on the other hand, simulations for a topological system show that the emission is a very regular, very localized on the edge, and keeps going around the system with a frequency distribution which is really a delta distribution. I have not plotted the frequency distribution of this emission because it's just a very trivial delta. Nothing interesting, but very interesting for applications. This is really a single mode laser with a very good slope efficiency. What I mean by slope efficiency, I mean that the energy is very efficiently funneled from the pumping into the lasing mode, which is a very good feature for a laser. And in particular, this chiral propagation is very much immune to disorder. You can imagine from what I showed you before, if you put some disorder here, lasing mode will just go around, will not be mostly affected in a too strong way. Of course, we as theorists, we like to go deep into all the finest details. And my student Matteo.
Can I actually ask a question? Sorry, I don't.
Of course.
So when perhaps you have this here, but when you talk about lasing, I mean, you showed a couple of examples. In some cases, it's basically just around the circumference. And in this case of the United States, it was basically outcoupled, which Boubacar has done. So I mean, if you outcouple it seems to me that this is just basically a normal laser, and you don't need the topological. So what is actually are you interested, or are people interested in the lasing just to see whether you can do it in such a system, or is there an advantage to do it here as opposed to a normal laser cavity?
Susanne, just wait 10 minutes and I hope I will convince you.
Thank you.
Good. So here it just lases around, you put some disorder and it keeps lasing in this edge mode. Of course, there are some interesting details which are interesting for theorists. some long relaxation time, some discrete modes along the edge, like it happens in the ring lasers, the collective excitation modes, which have some funny structure. Or there is also, sorry, what happened? So other intriguing surprises is some peculiar features of the laser threshold because of the fact that light is propagating through the amplifying region and is not just going back and forth through the amplifying medium. But these are somehow details, and the really exciting things happen when you start looking at the coherence of this topolaser emission. First, let's consider the case of a clean system. So in this case, one can use the theory of laser operation in spatially extended systems, as it was developed by a few people in the last years, including Ehud Altman, Sebi Dil, Michiel Wouters, Leonie Canet, Anna Minguz, and other people in non-equilibrium StatMech, who basically realized that the coherence properties of a laser, which consist of an array of many individual sites, if and only if one is able to get them phase locked, which is not a trivial thing, as I showed you before. Suppose you are able to get them phase locked, one knows that the coherence properties of this system follow the physics of Kardar-Parisi-Zhang physics, which is a well-known of non-equilibrium StatMech, with in particular some peculiar scaling properties of a phase coherence, with some power laws which are very well known from statistical mechanics. And here my student Ivan, in this paper, was able to find that indeed for the 1D chain, this is the coherence function indeed follows the scaling properties that one expects from the KPZ physics. If one does the same calculation for a topolaser, one has the great advantage that the lasing stays phase locked between the different sites in a very much more robust way. So here is not a problem to get the system phase locked, but at the same time, one gets exactly the same kind of KPZ spatio-temporal scaling of the coherence properties, which is a kind of interesting result for theoretical physics, because it means that this topolaser system are a very robust platform where to study the statistical mechanics of this KPZ model, which is an interesting thing for fundamental science, with the further advantage that this system is automatically with periodic boundary conditions, which makes life easier for us theorists because it reduces all the problem of edge corrections to the statistical mechanics. So here is just a finite size effect with periodic boundary conditions, which is extremely interesting for theory. Good. But looking more in detail into the coherence of the emission, what Ivan realized is that there is a very interesting behavior on the long time dependence of the coherence on the time. So, you know, whoever is interested in laser physics is interested in looking at the line width of the emission, which corresponds to the characteristic decay time of the phase coherence at very long times. So what Ivan did in these simulations was to take very long time and look at the decay of the coherence for time going to infinity. And what he realized is that for very large systems, there is the power law predicted by the KPZ physics stays very well. It's very well reproduced. Here you see these maxima. All these maxima fall on this blue line, which corresponds to the power law of KPZ physics. If you go to smaller sizes and even smaller sizes, this power law is replaced by a behavior which is closer to an exponential. So here is this power law, which basically is a stretched exponential in experimental terms. It moves towards an exponential. So if the system is small enough or alternatively, you go to extra long, hyper long times, you see that the coherence time recovers an exponential, no, the decay of coherence recovers an exponential decay. An exponential decay is known from everybody who is in laser physics as the Shaplov-Towns line width of the laser. So the natural next step for us was to check whether the Shaplov-Towns line width is followed by this topological laser device. And what we found is that for reasonable short sizes, the characteristic time of this exponential decay follows very well the Shaplov-Towns line width. If you go to very long systems, there is a departure. So the coherence time is shorter than one would expect for Shaplov-Towns. This was a very big mystery for some time, but Ivan was very smart and very deep in his reasoning to pinpoint what is the actual reason for this. And actually, the reason is that the Kardar-Parisi-Zhang model of the phase dynamics of this system is an intrinsically nonlinear model. So whenever you have a system which is big enough, the physics will be dominated by these nonlinear corrections which are intrinsic of the Capizzi physics, and which make this increase of the coherence time with size to deviate from the linear growth, which is typical of Shaplov-Towns. What Ivan is doing now, together with another friend of ours, Alessio Chiocchetta, is to study the dependence of this large system behavior. And their guess at present is that here the dependence is a square root. Square root dependence on the size of the system. They're using some sophisticated normalization group techniques that I fail to understand, but it's really advanced statistical mechanics. They seem to be able to provide statistical mechanical explanation for this peculiar behavior. So up to here, the one would not be too much surprised. This is the physics, which is quite similar between topological models, topological lasers, and standard lasers. Still, one has to think of one issue, is that for a non-topological system to follow this kind of rules, one needs that the different sides are phase locked. So the emission of the extended laser be really a single mode one, which is a very non-trivial thing to obtain in an extended array of lasers. For topological lasers, this comes somehow for free. So this is the free lunch that topological lasers seem to offer. But there is one more free lunch, which comes here, which basically is the robustness of this topological laser against disorder. So here we made a plot as a function of disorder of the coherence time. Blue and green are non-topological chains. And we see that even if at very small values of the disorder, one is able to keep the system emit in a single mode way, as soon as the disorder becomes of the order of the line width of the emission, of the order of gamma, gamma basically sits here, one gets that the coherence is broken. Basically, the coherence time becomes almost zero. So the emission becomes almost fully incoherent. You see here that the different sides of the lattice start emitting at a different frequency. So this gives a sort of mess of different lines, chaotic behavior, so no coherence is present. On the other hand, this is a topological laser emission. You see here that the topological laser emission is robust up to disorders which are of the order of J. Basically, as long as the disorder reaches the band gap, the width of the topological band gap. So as long as disorder is not able to cross the band gap, you see that the coherence is very well preserved. And here the emission remains very well monochromatic. And this is really a key result for applications, because it means that this kind of topological lasers can be used as a very efficient platform for emitting coherent light in platforms which may have some disorder, like semiconductor platforms.
So when you talk about this disorder, like physically, like you just said in the semiconductor, like what would that, like could that be?
You could, here we modeled it as different sites having a slightly different energy.
Okay, so just a spatially varying.
Yeah, spatially varying energy. But you know, it seems to be a completely insensitive to a spatial kind of noise. Whatever you have, the same happens.
Okay. Mm-hmm.
So this is really a killer result for topological lasers, because it means that the system is really robust against disorder, not only for what concerns the shape of the mode, but also for what concerns the coherence, which means the resilience to quantum and thermal fluctuations. So this
just
is
a quick question.
Yes, please.
So in some of these earlier experiments, I think the band gaps that they were able to open in the optical domain were really small.
Yeah.
And I think there was a little bit of controversy at the beginning of like whether that's too small to really compare to, say, like the line width and whatnot.
Yeah, you're perfectly right. So actually in Boubacar's experiment, it's not fully clear why the system is so robust to anything. The topological gap is so robust because the gap is really tiny. So the thing that surprised a lot of readers of the papers is that the laser emission is much broader than the topological gap. So actually, in my opinion, there is no real problem in this, because you know that the laser emission can be much narrower than the emission of the cold modes, because the Charlotte-Towns line width is much sharper than the line width of the bare cavity mode. So there is no problem of having topological lasing, even if the system has very broad bands, because the laser itself is able to narrow down the line width so that it fits in the topological gap. So the fact that the laser emission in Boubacar's experiment is very broad may be due to the fact that the system has a temporal inhomogeneous broadening. Basically, with the temperature of the device may be fluctuating a lot in time. So when you integrate the line shape over long times, you see a big line, but at every single time, the line width is very narrow. It's just that it moves in time while the system heats or cools down during the experiment.
I see.
So this, please.
Yeah, thanks a lot for the answer.
No. This is my view, but it's still something which is under discussion. Good. So this is basically all I want to say about these topolasers. Let me move quickly into the strongly interacting photon fluids, where basically the key ingredient is the so-called photon blockade, which basically means that whenever you have a cavity where the interaction, so the nonlinearity is so strong that a single photon is able to shift the cavity mode by more than the cavity line width, you have that a single photon can be injected in the cavity, but a second photon cannot. So the second photon cannot enter the cavity because its energy would be blue shifted a lot by the very presence of the other photon. So in this way, the cavity behaves as a support for effectively impenetrable photons. And this physics is completely at odds with what one normally has with non-interacting photons or Maxwell equations, where photons are able to cross each other without seeing each other. So what happens if one combines these strong interactions with synthetic gauge field for photons? For instance, in a Harper-Offset model. So here is a simulation of a spectroscopy experiment where one drives the cavity with a given frequency, and this frequency is resonant with the frequency of a laughing state for photons in this magnetic environment. So one sees peaks for the photon population, which exactly match the position of the energy of the fractional quantum Hall state. And indeed, here you see that the overlap of the photonic wave function in the system has a very high overlap with the wave function of laughing state for photons in this geometry. So this is a way to generate a laughing state for a few photons. Experimentally, rather than using these lattices, it seems simpler to use a cylindrical geometry as first proposed by Onur and experimentally realized in the group of John Simon at Chicago, where he was able to invent a far smarter design than us theorists. Oh, sorry, I did some disaster. Here, okay. A far smarter geometry as compared to what us theorists imagined, which is a non-planar cavity with built-in synthetic magnetic field for photons, which has some crucial technical advantages. And by pumping the cavity at a given frequency, he was able to generate a two-photon laughing state. So if you don't know about topological physics, you can understand the two-photon laughing state as a linear combination of having two photons in the same mode, with two photons being in modes with opposite angular momentum. So you can imagine a laughing state, which is Z1 minus Z2, Z1 minus Z2 square. In the language of optical systems, can be seen as two photons being in the first mode, with a state with one photon being in the zero mode, and one photon being in the two mode. What John did here was a more subtle realization of this physics, using modes with different angular momentum, which are multiples of 3. So here he pumps two photons in the L equals 6 state, and the signature of having a laughing state is that he has photons in a proper many-body superposition of this form. Laughing equals 6, 6 minus 3, 9. And this state is the only one which is energetically separated by all other possible two-photon combinations. So this is an energetically isolated laughing state that is able to address in a spectroscopical way. So putting a laser beam which is resonant with this transition, but is not resonant with any other transition with other two photon states, is able to selectively excite this state. So in order to check that this state is really the one which is excited, he made some correlation and measurement in the emitted light, selecting the different angular momenta, and in agreement with this paper by Onur, I could find exactly the correlation signature that one expected. The problem of this setup is that it's very hard to move on to higher particle states. So one needs a more subtle pumping schemes that I have no time to discuss in detail, but have led to very interesting realizations of Mott insulator states of photons on a circuit QT platform, again in the group of John Simon in Chicago. So let me conclude with a few words about what new many-body physics could be done with these systems, which is basically what I'm presently up to. So the question is, how can one use these systems to observe anyonic statistics? So here is an first experiment done with circuit QED, which was able to see the interplay with strong interactions and strong synthetic magnetic fields. And this experiment basically is the photonic analog of what has been done in the group of Marcus at Harvard, using cold atoms in a two-leg atomic ladder in his atom microscope. He is done in a 3-site photonic system with circuit QED in the group of Pedram at the Google Labs. So I was able to see that one photon circulates in this direction, two photons, or alternatively, a single hole propagates in the other direction because of this interplay of magnetism and interactions. So along the lines of this kind of experiments, we try to figure out ways to detect an anyonic braiding phase. Here is a first attempt by Onur, just braiding two holes around each other, where one can see the many-body Berry phase associated to the braiding of two quasi-holes as a relative phase between the no-photon and the two-photon state in John Simon's cavity. So in optics, the correlations, the coherence between states with different number of particles are optically accessible. It's just optical coherence. So in this way, one can probe many-body Berry phases, which of course would be very difficult in atoms or in electrons, because one cannot build superpositions of states with different particle number. Other techniques to do these kind of experiments, which do not involve manipulation, are related to the structure of states with quasi-holes. So here is a numerical simulation using 3 tensor network methods of the structure of quasi-holes, single quasi-hole, double quasi-hole on a lattice. Is a fractional quantum hole obtained by Hopper-Hofstadter with some non-trivial magnetic field. And Elia and friends were able to compare this size with the theoretical prediction for quasi-holes. And they show that the Berry phase, the braiding phase, tends to the value, that one expects for these fractional quantum hole phases. Last effort, which was done by Alberto together with Elia, was to study anyons as quantum mechanical particles. So normally in laughing states, anyons do not have an independent life, but if you dress them with some extra impurities, you can create some anionic molecules, which are on the family of polarons. So say, whenever you have an impurity in a quantum gas, this impurity can bind with some quasi-hole and create a polaron. Here is a new family of polarons called anionic polarons or anionic molecules, where one binds, say, a heavy atom to a quasi-hole in a fractional quantum Hall gas of light atoms. And one gets an Hamiltonian which has more as this form, with an effective mass which comes from the mass of the impurity plus some correction from dragging effect. And the magnetic field is a combination of the charge of the impurity and the charge of the quasi-hole. And you know that the charge of a quasi-hole is fractional. So just by looking at this cyclotron orbit, one could infer the fractional charge of anyons in the bulk. And this is very different from what has been done so far with electrons, where most experiments, except for one by Mott at Weizmann, all other experiments in fractional quantum Hall in electrons have addressed the edge. Here is an experiment in the bulk. So here is fractional statistics, which is different from fractional charge. So how to see fractional statistics? So the idea of Alberto and Elia was to just study the collision of two such anionic molecules. Whenever you have a collision, you have two channels available. One is a direct channel in red, and one is an exchange channel. Whenever you have indistinguishable particles, the two channels sum up in amplitude. So you may have interference effects. And what the guys found is that the fringes that one sees in the differential scattering cross-section as a function of the scattering angle, so the position of these fringes depend on the fractional statistics of these two anyonic molecules. So depending on the fractional statistics of the underlying anyons, one sees fringes at different positions. And the position of the fringes just scrolls as a function of these fractional statistics. So just by looking at the position of these fringes, one can infer the fractional statistics, which has never been done so far for particles in the bulk. There is just a couple of experiments on the edge that have come out last year, one in Science in spring by the group of Gwendal-Febvre in Paris, and the second one is by Michael Manfra a few weeks ago in Nature Physics. Here it will be different because this is a physics in the bulk. So this is a very challenging experiment, but it will be conceptually very, very interesting. And for me, it was the way of understanding that mysterious object of anyons. So just to move to conclusions, we have presented one body physics in synthetic magnetic fields, topological lasers, and the first steps in the direction of strongly correlated many-body physics. So there are many interesting challenges ahead of us, which can be direct signatures of fractional charge and statistics in photonic fractional quantum Hall systems to go real for the experiment, to understand how big one can create the systems and what are the ultimate limitations in creating these fractional quantum Hall photonic systems. And the long-term dream would be to upgrade to systems supporting non-abelian anyons and to see how robust is the topological degeneracy of the ground states of these systems, with an eye towards topological computing applications. So if you want to know more, this is a few review papers that I suggest you for further reading. And if you are really interested in this physics, as I really hope, just save the date for this summer school that sanitary emergencies, if the sanitary emergency allows us, we will organize in Varenna on a wonderful location on the Como Lake in northern Italy with a number of very exciting lecturers, including some among the leaders in the field. So you will be very much encouraged to apply to this wonderful summer school next summer on the Italian lakes. Thank you very much for your attention.
Thank you very much, Iacopo, for this very nice talk. So are there questions from the audience? So then just unmute and speak. So maybe I can start with the question, like with the scattering of anyons, like how would you, like is that some, like how would that even, like how can you understand that? How can you do that experimentally, really? Like taking these two anyons and making them scatter and then detecting kind of like in a directional dependent way the scattering amplitude?
Yeah, I would do something at the simplest level. This would be the idea. You take two heavy impurities in this fractional quantum Hall system. You make them bind to some quasi-Hall, which is not such a trivial task. I think the simplest way would be to have an impurity outside and send it slowly inside the cloud so it can capture a quasi-Hall when entering from the edge. Mm-hmm. So then you do the same on the other side and you send them head-on collision. And then you measure how they distribute in space. Like normal LHC experiment.
Like an LHC, okay, yeah, right.
Of course, there is a string of hypotheses that you have to make, which basically boil up to having very heavy impurities in a very light of gas of atoms. So very heavy impurities and very strongly interacting. So the best option that we found so far is for ultra cold atom system using polar molecules. So you take a molecule of, say, rubidium and strontium. So they have a very strong dipole, electric dipole moment, so they interact a lot.
Mm-hmm.
And you send them very, very slowly against each other and look how they scatter.
Right, yeah.
A small scale LHC experiment.
Tabletop LHC, that sounds very good, yeah.
But I have one question. You alluded to the role of interactions in these photonic blockade systems. What role the interactions play in these topological lasing, or do they?
In a sense, in topological lasing, they at this level they play no role. In a sense, all these calculations were done with the only interaction between photons being the gain saturation. So this has to be there because any lasing medium is intrinsically saturable, otherwise it would not be lasing. But that's all. If you add some photon-photon interactions, things become more complicated. So the system can be prone to secondary instabilities, which actually so far has never been observed. So the systems seem to be experimentally robust. In theory, it's not always the case. In theory, if you are unlucky enough, you can get the system become dynamically unstable and it gets to some chaotic emission state. But we would not, in a sense, expect that interactions, as long as the system is not destabilized, would play a really dramatic role. So my students are now up to including the interactions in the model and trying to figure out what's happening. For the moment, I would say that nothing major is happening. Of course, the long time line width will no longer be just the Charlottowns, but it will be enhanced by the so-called Henry factor of semiconductor lasers, which is well known for semiconductor lasers as soon as you have a non-trivial dependence of the refractive index on the light intensity.
Mm-hmm.
More questions? Maybe since we just saw this picture, so you showed us a lasing mode at the edge of a one-dimensional chain, and we saw a one-dimensional edge on of the two-dimensional system. Is there some, I mean, is it possible to also have a two-dimensional lasing edge mode of a three-dimensional laser?
This is a really great question. I've been thinking a bit what would happen, for instance, if you get some Weil state, some say Fermi-Arc state to lace in the edge of a Weil system, or more complicated configurations. I have really no idea what could happen. At the first glance, I would say that something similar to here would happen, with the additional problem that you have the lateral dynamics, which gets important. But I really cannot tell you more than this. Is a very interesting question. And the physics would become even more interesting if you consider the three-dimensional edge state of a four-dimensional photonic topological insulator with synthetic dimensions.
Wow, that's okay.
But no, jokes apart, Motti Segev, he's an extremely creative guy, as many of you know. He has just come out with a paper on PRX not long ago, studying this topological lasing combined with synthetic dimensions as a way to obtain topologically protected mode locking in lasers. So you know that mode locking is a key concept in laser physics because it allows to obtain functionalities of laser which are of great importance for applications. So his way of getting mode locking topologically protected is extremely exciting. So you could think of having a three-dimensional system So where you exploit the two-dimensional geometry to have a lot of sites. And then the third dimension would be the synthetic dimensional to obtain mode locking.
Cool. Yeah.
I only need to find a brave student to be able to do the calculations, which are too hard for me.
Okay, so maybe we hear about that in the next talk. So,
yeah.
Are there more urgent questions or any urgent questions? If not, then I would like to thank Iacopo again for a very nice talk and announce next week's speaker, who is going to be Tommaso Macri, speaking from Brazil. So everyone is again welcome to join. And with that, thank you, Iacopo. Thanks everyone for being here.
Okay. Thanks a lot. Thanks to all of you for listening. If you have any kind of question, here is my email. Just don't hesitate in writing me whatever question or whatever objection you may have on this physics as well as